Hello everyone, I'm Junji Yu. Today I'm going to share our work, Context-Based Cluster Photo Localization. This is the agenda of this presentation. I will start with introduction, followed by the background, approach, the results of our experiments, and I will give the conclusion in the end. Software debugging is a time-consuming but important task in the process of software development and maintenance. To reduce the debugging costs, researchers have proposed various localization techniques to provide automated assistance in finding faults that code failures. Spectrum-based photo localization is a classical one, which is also called as coverage-based photo localization. Spectrum-based photo localization calculates the spatialness of each statement by analyzing coverage information and error vector to identify faulty statements. Deep learning-based photo localization has recently become a hot research direction in photo localization due to the fact that neural networks have shown their powerful ability in many areas. Figure shows the architecture of deep learning-based photo localization. Input layer, deep learning component with several hidden layers, and output layer. DLFL use neural networks to learn a photo localization model to evaluate the suspiciousness of a statement of being faulty. Coincidental correctness, which called CC, represents that a test executes faulty statements coincidentally, but the result is right, which will affect the result of the photo localization. As the figure shows, CC are prevalent in programs. Program slicing technique selects the subset of statements which affects the output value of a following test by extracting data and control dependence of statements to construct context information. As the example shows, a dynamic slice has a smaller size and is related to a specific execution. Therefore, we use dynamic slicing to construct a final context. From the above analysis, we propose an approach for localization named CBCFL. According to the runtime information, by executing all the test cases and using dynamic slice, we can obtain raw data and the final context. Our approach includes two stages, namely constructing a final context and identifying CC tests. The first stage is constructing a final context which takes the raw data and the final context as input and output context metrics after filtering irrelevant statements. The following stage will use the cluster algorithm to find the CC tests. After clustering, the label of cluster which are identified as CC tests will be changed into failing tests. After two stages, the output data will as the input of SFL and DLFL. To evaluate the effectiveness of CBCFL, we use the cluster algorithm with raw data to identify CC tests as the baseline. We evaluate our approach on 6 real-world programs with all real faults. All the programs are from Difficult4J. Our evaluation metrics include the number of top key, mean first rank, and relative improvement. And the baseline includes two kinds of localization techniques. For SFL, they are D-star OGI bilayer, and for DLFL, they are MLPFL and CNFL. The first research question is how does CBCFL perform in identifying CC tests compared with baseline? To evaluate how effective our CBCFL is at identifying CC tests compared with baseline, we use precision, recall, and FE as the metrics. From the table, we can observe that CBCFL perform better than the baseline in identifying CC tests. The second and third research questions are how effective is CBCFL compared with state-of-the-art SFL and DLFL, as shown in table. For all metrics and all the SFL, DLFL, the CBCFL get the same or better results in comparison with baseline respectively. What's more, compare the MFR metric of the 5 approaches in the baseline and CBCFL scenarios. From Figure 7, we can observe that CBCFL improves the baseline a lot in either approach, and under the RIMP metric, we can find that to locate the first 40 statements, the number of codes to be checked using CBCFL is less compared with using the baseline. Here are our conclusions. We propose approach CBCFL for localization. The key ideas of CBCFL are using dynamic slice to obtain context matrix, identifying city tests by cluster analysis based on this context matrix, changing the label of city tests into foreign tests. We implemented our idea and evaluated CBCFL on real-world datasets. That's all. Thanks.